Hello, everybody. Welcome to Mankind in Training. I am your host, Joshua Parr. Today I have another Python example. We're going to solve some problems with the Scipy library. Let me share my screen here. Mankind in Training presents a Scipy tutorial by me, Joshua Parr of Finlay Analytics Data Science Company. The very first thing we're going to do is import NumPy as NP, import matplotlib.pyplot as PLT, and import SciPy as SP. And from the SciPy library, .optimize, we are going to import the minimize function. Say we want to minimize this function, f of x equals x minus 3 squared. We would define the function, f of x, and have it return x minus 3 squared. And then we're going to create a variable called the resolution and make it equal to the minimize function, f x0 being equal to 2. And then we're going to resolve x, and it will give us 2.9999. Now, say we want to minimize f of x and y being equal to x minus 1 squared plus y minus 2.5 squared with the following bounds and inequalities: x minus 2y plus 2 being greater than or equal to 0, negative x minus negative 2y plus 6 being greater than or equal to 0, negative x minus or plus 2y plus 2 being greater than or equal to 0, and both x and y being greater than or equal to 0. And this is how we're going to type this in. We're going to create a variable f with the lambda function, x0 minus 1 squared plus x1 minus 2.5 squared. And this is how you're going to type in the inequalities. Type colon INEQ, comma, fun. Make sure they're tagged in within the parentheses or the quotation marks. Equals lambda x, x0 minus 2 times x1 plus 2. That's how you put the inequalities in. And then we have to give it bounds. In this case, we have 0 and none for x and y. And then we are going to create a resolution with the minimize function like above, with bounds and constraints. And if you ask for the resolution of x, you'll get this array for x and y. It solved it for you. Now I'm creating an array x, a linear space from 0 to 10 with 100 values, and y being equal to x squared times sine of x. I'm creating a scatter plot of all of the values of that function. Now I want to find the values in between these points, these data points. So in order to do that, I'm going to import SciPy's interpolate, inter p1d, f equals inter pd, x, y, and we're going to make this kind a cubic fit. I'm creating an x dense and a y dense. And I'm plotting the line, and I'm plotting the individual data points over top of the line. Now, I did it cubic here because I wanted a smooth return, but sometimes you need a linear interpolation. They just don't always fit well with a smoothly curved function like the one above. So this is what happens when you try to do a linear interpolation of this data. Linear works great if the curve, if there is like no curve to it, if you can find a straight line to fit the data well. But so now I am creating another array x data linear space with 10 values in between 0 and 10, and some y data, 3 times the x data squared plus 2, and creating a scatter of the x data and the y data. Now to fit this data to the curve y equals ax squared plus b and find the values of a and b. All right, we're going to use scipy.optimize and import the curve fit function. And we're going to create a function x, a, and b and return a times x squared plus b. And we're going to create pop t and p covariance equals the curve fit function of the x data and the y data, p0 being equal to 1 and 1. And when I typed in pop t, I got the answer. And if you want to get the covariance, you type in pcov, it will give you that as well. So now here we have the spring motion equation. It's as follows. Y of t is equivalent to a cosine omega t plus phi. To find the frequency of the oscillation omega, I start with creating a t data array and a y data array. And I'm going to plot the t data and the y data. And when I did that, we got this, and it looks like omega being equal to 2 pi f, f being equal to 1 over t, and t being approximately 2. So omega equaling 2 pi times 1/2 equaling pi, and a equals 4 and phi equals 0. With this information, I will create a new function to put into the curve fit. It will have all the parameters x, a, omega, and phi, and it will return a times cosine omega times x plus phi. I'm again creating a pop t and a p covariance with the curve fit function. And when I call pop t, it gave me my array for what I was asking for. It answered my question. And for my p covariance, I type it in and it answers my question. Here, I'm taking a, omega, and phi and making it equal to pop t, and t being equal to another linear space array, and y being the function. And I'm plotting the line and I'm plotting the data. And now I have the real data and the real line for this equation. If I ask for the pop t, returns it. If I ask for the y or the t array, it will return them. If I ask for the covariance, it will return that as well. So if I want to find the estimated error of my parameters just now, I will take the square root of the diagonal matrix of the covariance, and that will return my answer here. Now we have some Legendre polynomials, p sub L of x satisfying 1 minus x squared y double prime minus 2xy prime plus L plus 1 y equals 0, and the angular component of the spherical Schrodinger equation, which would permit non-infinite solutions. Now I'm going to import the Legendre from Scipy special. I'm creating a linear spaced array again from 0 to 1 with 100 values, and I'm plotting that array. And I'm using the Legendre function. Now I have a Bessel function that is j sub alpha of x, satisfying x squared y double prime plus xy prime plus x squared minus alpha squared y equals 0. And I can find Laplace's equation in polar coordinates by importing jv from Scipy special and doing something similar. Putting x against jv, 3 and x, and plotting. And now I have the Laplace equation in polar coordinates. So now we are going to do some calculus. I'm going to import Scipy's miscellaneous, from Scipy miscellaneous, I'm going to import the derivative function. And I'm creating a function f of x that's going to return x squared times sine 2 times x and the exponent of negative x. I'm creating another linear space array from 0 to 1 with 100 values. Now I'm plotting x and f of x, and I'm finding the derivatives, first and second derivatives, and plotting them all together. The function and the first and second derivatives all in the same grid. And now if I want to integrate, I will do it like this. We have an integral from 0 to 1, x squared, sine 2x, e to the negative x dx. From scipy.integrate, import quad. I'm going to create an integrand with the lambda x squared times sine of x, sine of 2 times x times the exponent portions of negative x, and integral. An integral error I'm making equal to the quad integrand 0 and 1. And then when I call for the integral, it gives me the answer. And here, a double integral from 0 to 1, and then again from negative x to x squared. I'm doing sine of x plus y squared dy dx. And if I want to do that, I import double quad from scipy.integrate, and again create an integrand. And now I'm going to create a lower y and an upper y. Negative x squared, and then again I'm creating an integral and the integral error, and making it equal to double quad the integrand 0, 1, and the lower y bound and the upper y bound. And when I ask for the integral, indeed I get the answer. Thank you guys for watching. The next ones I'm going to be doing are differential equations with SciPy again. And then after that, I'm going to do a full deep dive into C++ and Python courses. Thank you for watching Mankind in Training. If you like, subscribe. I am Joshua Parr. Thank you for watching.